the speed of light. And so whenever we're looking at objects that are further away from us, not only are we mapping things out in space, but we're also mapping things out in time. So whenever we measure the light from a galaxy that's very far away, then we are we are able to understand how the expansion of the universe changes in space and in time. And so DESI, which I'll explain what that is exactly, is trying to make a map that looks something very similar to the right. With using the things that we can measure, i.e. the galaxies, we're able to understand how things have changed in time and space. Okay, so I said that we're going to use two attributes of galaxies, two attributes of ordinary matter. Cheers, yes. Choo-choo! I think it's coming over here as well. I see the lights. All right, excellent. So everything in the universe is moving away from everything else in the universe. The universe is expanding and accelerating in that expansion. And when an object is moving away from us, it redshifts. Redshift is very similar to the Doppler effect, something that we kind of heard just now. When the train goes by, a change in the frequency, change in what you hear, like that effect is the Doppler effect. A similar thing happens with light. And of course, depending on how fast an object is moving, that effect is different, right? It sounds different when a train is moving by, or a car, or a race car, right? That change in frequency is something that we can measure with our ears. Same thing that happens with light. When a galaxy is moving away from us, the speed at which it's moving away from us can be measured in how the light is stretched out from us. It's redshifted. And so when we look at the galaxies, we can get a sense for how quickly they're moving away from us. A trickier measurement actually is how far away those objects are from us. There are two main ways that we measure the distance from ourselves to objects in the universe. One is called standard candle, and this has to do with supernova, which we'll hear about later. But type 1A supernova are pretty much, when they explode, they have the same brightness. And so we know exactly how bright they should be, and so if we measure one at one distance or another distance, depending on how the brightness changes, we can evaluate how far away that supernova is from us. Standard candle, right? You have a candle here, or you place it on the other side of the room. Depending on how much it dims, you can evaluate how far away. Oh, the train just keeps coming. All right. Another way is a standard ruler. If you place a ruler in front of your face, it subtends a certain angle. And if you move that ruler to the other side of the room, it subtends a much smaller angle. And the differences in that angle you can use to understand how far away that ruler is placed. But unfortunately, there aren't a lot of great rulers in the universe, meaning galaxies are not the same size. So if you were to look at a galaxy close to us and one further away, you can't necessarily assume that it is the exact same distance across, right? So it took quite a long time to find a true standard ruler in the universe that we could measure things to. And one that we use is baryon acoustic oscillations. So that's why I told you ordinary matter is baryonic matter. This word comes up again, baryon acoustic oscillations. And I'm just going to say a little bit about baryon acoustic oscillations because this is how DESI will measure distances in space. But based on the early physics of the universe, there is a more than random chance of two galaxies being separated by a certain distance. You see these pictures here. It doesn't look like this exactly. This is a cartoon, of course. But for the most part, galaxies are randomly distributed, but there is a more than random chance of finding two galaxies separated because of what happened early in the universe. And I keep saying more than random because this is a statistical measurement. And when you hear statistics, it means you need a lot of measurements. We need to measure as many possible galaxies to actually be able to measure this more than random occurrence. But when we do so, if we were to slice up the universe in kind of sections between us and the edge of the universe, or rather between us and where we can't see anymore, which is a lot closer to us than the edge of the universe. If we were to do that and we were able to measure the distance to those based on this, we could compare the separation of galaxies to what we knew they were with the cosmic microwave background. This is a little more detail that I want to get into right now, but the baryon acoustic oscillation is our way to determine distances between ourselves very accurately and different slices in the universe. So together with the baryon acoustic oscillation measurement, using that as a distance measurement, and redshift, we are able to create a three-dimensional map of the universe. Okay, so that was the dark energy side of things. I want to pause here for a trivia question, and then we'll get into the spectroscopic instrument part of things. So my question is, in 2011, Saul Perlmutter, Adam Rees, and Brian Schmidt were awarded the Nobel Prize in Physics. For what discovery were they recognized for? I'll read them and then I'll call on you, sir. A, the event horizon of the black holes. The universe is accelerating in its expansion, the cosmic microwave background, or dark matter halos. Any guesses? You go ahead. That's correct. Yes, it's B. Yeah, great job. And I just want to pause here and talk about this for just a second. At the time, the general consensus was that the universe was not accelerating in its expansion. And in fact, this discovery made by two different teams really changed the trajectory of cosmology in general. And I think it's so fascinating because that's so not common, that an experiment or a measurement makes the field of a science go in a completely different direction. So it's extremely exciting that everyone working on this project thought they were going to get a different answer than they got. And the science is able to speak for itself. And now it has sent us on a path to understanding what is causing that acceleration. And that's why I have a job. So I'm glad that they discovered that. All right. Cool. So we're going to get now to the spectroscopic instrument side of things, which is what I love to work on. I really enjoy working on instrumentation and hardware, and it's a big part of the reason I came to Tucson, because there are so many telescopes here and so many instruments that we can work on. But I want to clarify what I mean by instrument. So a telescope is basically a big bucket for light. And an instrument is something that does something interesting with that light. It takes the light from the bucket and it measures it in a way that helps us understand a scientific goal. Spectroscopy is measurement of light as a function of wavelength. And so what we do is we capture that light from the telescope and we spread it out with a prism essentially, and look at the light as a function of wavelength. This is in comparison to an imaging system that just takes pictures of galaxies, which is great, something that Hubble does, for example, and a lot of instruments do. They take very detailed images of things. Instead, we're taking that light and then chopping it up and looking at what's inside of it. So DESI is not the first experiment to want to make a 3D map of the universe. We're just the biggest and best and newest, let's say. But before us came a BOSS, a Baryon Acoustic Spectroscopic Survey, and BOSS had 1,000 optical fibers that they would stick into a pre-drilled plate, and then that plate would be installed on the instrument, and then the telescope would move, look at a part of sky, and the light from 1,000 galaxies would go down each one of those fibers. Let me just show that again. So that's a person plugging in 1,000 fibers. And they had maybe 8 of these plates per night. And so when Desi came around and said, well, we want to do more, they said, no, we're not going to plug more than 1,000 fibers in a plate. We've got to come up with something new. Because BOSS measured, oh no, what have I done? BOSS measured a total of 3 million. Sorry. Oh goodness. Sorry, 1 second. So BOSS measured a total of 3 million spectroscopic redshift. Well, DESI wants to do 35 million, so a whole order of magnitude more. So we need a new approach. This is what DESI looks like. It's on the 4-meter telescope up at Kitt Peak, the Mail telescope. So if you haven't been, hopefully when things open up again up there, you'll be able to check that out. It's the big one sticking off the top of the mountain. The mirror is right there down at the bottom. And so when the dome is open, the light comes down, bounces off the telescope here, and then up to what we call the focal point, obviously where the light focuses. And at that point, where the focal point is, we have 5,000 robotic positioners. And obviously I'll show more of that. So the light travels through 1 meter optics, about 6 of them, and it kind of corrects the light as it goes through. Then it hits these 5,000 fiber optics. Then the light travels down the telescope along 40 meter stretches of optical fiber to spectrographs that are sitting down here on the floor in a special room that's nice and cooled down to make sure everything's stable. And what we have down there are 10 3-arm spectrographs. And what I mean by 3 arms is it has 3 different detectors in them. The reason for that is, we have kind of night goggles help you see at night. There are thermal cameras, there are optical cameras. There are different sensors that are good at seeing different wavelengths. And so we want to use all of those types of sensors so we can see as many wavelengths as possible, not just the optical wavelengths that our phones or CCD cameras take pictures of. So the workhorse of the instrument are the 5,000 robotic positioners. And so they have 2 motors each. It moves the positioner around, and then the fiber is connected here at the top. And so the fiber can be moved anywhere within a 12 millimeter diameter circle. And so what happens is all of the fibers are moved to coincide with a location on the sky, a galaxy, and then 20 minutes later, they're all moved again. And so in this way, we're able to see many more galaxies than something like BOSS, where they actually had to plug in these fibers. So here's me testing this in the clean room back at Berkeley. So I basically followed the hardware from Berkeley here to Tucson, making sure every single one of those positioners worked. You see just a slice of it. We made 10 identical slices and put them, shipped each one of them here to Tucson, and then installed each one. And we call each one a petal. So 10 petals to the whole focal plane. And this is kind of a sense of what it looks like when they're moving. Now they can overlap. they can run into each other. We don't want them to run into each other, but we want to make sure we can reach every single point on the focal plane. And so we use special algorithms to make sure that they don't run into one another on their way to getting to where we're telling them to go to. Okay, so I want to quickly guide you through how we get fibers on objects on the sky. So first what we do is we open up the telescope, the dome, and we say we want to go to this part of the sky. And so the telescope moves over there and we take a picture of the sky. That's what this is right here. It's a guiding image. And each one of the squares is around a star that could be used as a guide star. And so it picks a couple of these guide stars and says, okay, now we're locked in place because of course, we are moving relative to the sky continuously, but we want to make sure we keep staring at it. So the guide cameras are consistently giving information back to the telescope. It's like move a little, move a little, move a little, move a little, so that we keep staring at one place on the sky. And then it says, okay, I know I'm looking at this RA and dec, right ascension and declination on the sky. That's like Latin long, latitude and longitude on the sky. It says we're looking at this area. Okay, now we need to tell the positioners where to go in order to line up with the galaxies that we're trying to look at. And so we move the positioners, but the positioners move pretty well, but not perfectly to where we want them to go. So what we do is we take a picture of the fibers backlit. So we shine an LED back through the fibers, and after we've moved them, we take a picture, and that camera says, okay, you're almost there, but move a little this way, move a little this way, and a little this way. And so they make a correction move. They make up to 2 correction moves, and then they are exactly where we told them to be. And then when we know they are where they are, then we turn off the backlight LED and we take an image of the galaxies. And so this is what our data looks like. It's not cool like Hubble. It's not these beautiful pictures of galaxies, but each one of these stripes going from left to right is actually telling us so much about what's inside each one of those galaxies. So it's an incredible amount of information. And so we sit on looking at those galaxies for about 20 minutes. And then we start the whole process over again. We go to another part of the sky, move the positioners, stare at it for 20 minutes, and keep going throughout the night. The other night, we got more than 100,000 spectra in one night. So it's kind of way more than any other project's ever been able to get. Here's a little bit more on the spectrographs. So I explain why we have 3 of them, but we have 10 identical spectrographs. So each one of the spectrographs goes to 1 pedal. And so we have 500 positioners with 1 cable going to 1 spectrograph. So we kind of have 10 identical instruments, essentially. So DESI has been installed for quite some time now. It got first light on 2019, meaning we got science data down the fibers and collected that with the spectrographs. And so we don't take data of galaxies quite this large as the one that you see here, M33, but this was used as an example. So that galaxy takes up almost a whole pedal. Most of the galaxies that we're looking at take up only 1 fiber. So each one of the blue circles you see there is supposed to represent one of our fibers. And so the spectra you see here is the light that went down one of those fibers. And then we spread out the light and we look at how bright each one of the lines are. This can help us measure the redshift because if we know where these lines are supposed to be, and for the most part we do when something is at rest, when it's moving away from us, we can see how that wavelength is shifted, measure the redshift, but we can also measure a lot more. And so one of the great things about DESI is that not only are we going to be able to build up this map to help us understand dark energy, but we're also going to learn about 35 million galaxies and what's inside them and what's going on with each one of these astronomical objects as well. So we got a lot of data to work with, and it's pretty exciting. So we started building the map. What you're going to see here, every single one of those dots is the light, essentially the distance, the redshift to one of these galaxies. The colors indicate what kind of galaxy it is. The large red galaxies, or emission-like galaxies, or a quasar, or a bright galaxy, it's going to kind of twinkle around, and that's because it's actually moving across the sky kind of like this. And so we are starting to build our 3D map. And so this represents the data of just a few months. And so DESI plans to run for 5 years. And so in those 5 years, we expect to be able to build on this map over time and hopefully understand dark energy a bit better. So I believe I've used up all my time. So thank you very much. Any questions?
Oh, yeah. Thank you so much, Parker. That was great. Any questions? Yeah.
Spectrum beyond the visual. Where does it range to? Does it go down radio?
No, it is optical and near infrared. So it goes from like 350 nanometers to 980 nanometers. So it's not way outside of the visible spectrum, but enough so. But it doesn't go down to radio or yeah, not much beyond optical and infrared. And part of the reason for that is the instrumentation would have to be so different. So for example, radio telescopes are much larger. It just takes a lot different hardware, but the hardware needed for optical and infrared are similar enough that we can use the same.
Other questions?
Each one is, he asks, does each positioner track a galaxy or just a point in space? And so one thing I didn't mention is before the DESI survey started, we had an imaging survey. And so we had telescopes, the Mail telescope and the Bach telescope up on Cape Peak, and then also one in Cerro Tololo in Chile, imaging all of the sky that DESI is going to go after. And so it was able to identify all the galaxies we wanted to go after. And so we know where the galaxies are in RA and DEC space, like latitude and longitude. And so whenever we go to a certain area of space, we know where all of the galaxies are going to be. And so each one of the positioners is moved to align with that galaxy exactly. Now, I would say that the vast majority of the fibers are looking at galaxies, but there are a handful that are looking at stars. That helps us calibrate, make sure that we know how much light is going down the telescope. And some of them will look at sky as well, so blank sky, because we need to subtract that out. But for the most part, each positioner is moved to look at a specific galaxy.
One more question?
Sorry. It's a visual telescope. Do you have some way of compensating for interference?
We do not have, it's usually called adaptive optics, AO, right? That can maybe shine a laser up and see how the atmosphere is shaking in some sense. The Mail telescope doesn't have that. So, but we don't need it as much because when projects are trying to image something very carefully, they need it to be as still as possible. But for our case, since we're not imaging something, there can be a little wobble. We just need as much light because we're going to break it up anyways, right? So no, we don't have any way to kind of stabilize from the atmospheric wobble or turbulence. We do have to account for atmospheric absorption. And so that's why we take spectra of the blank sky, because then we know how much light is being both produced by the atmosphere and also absorbed by the atmosphere, and then we can take that into account. Yeah. All right, thank you so much.
Sure, thank you. All right, so now we're going to have a 20-minute introduction, intermission. So it is now 7:35. So let's come back at 5 till 8. During intermission, please grab another beer. We have telescopes out here by the train tracks that you can look at objects in the sky. Also, I want to call out my fellow graduate students here. I see them everywhere. You can ask questions. Raise your hand if you are able to answer questions about astronomy. No, okay, only a few of them are brave enough to raise their hands. Okay. Yeah, we'll see you back at 5 till 8.
I'm just going to assume that's a ramp because she just pointed out there. $2. Just saying. Okay. Give me 2 minutes. Or if you want to put your title sign up. What? Whoa! Look at that! It's fine. The one speaker is loud enough. Yeah, thank you. Oh, I didn't ask the undergrads if they.
I just want to plug for a second. I just went out and looked at the telescopes. The seeing is great tonight. You can see 3 Galilean moons, 3 of Saturn's moons. You can see the stripes on Jupiter. You can see gaps in Saturn's rings. It's awesome. Just want to plug that. 2-minute warning, folks. 2-minute warning.
Yeah, exactly. I was thinking that's good. Yeah, exactly.
All right, we're gonna go ahead and get started with our second speaker of the night. Come and grab your seats. Our second speaker is Rachael Amaro. She is a graduate student at Steward Observatory with me. She's one of my classmates. And she comes here from University of Illinois in Champaign, Urbana, right? And she studies supernovae, and that's what she's going to tell us about tonight. So please give it up for Rachael Amaro.
Hi, everyone. Thank you, Borderlands, for having me, and thank you, Parker, for that super interesting talk before me. I'm here to tell you about the history of supernova observations and also ask you to be kind, because I haven't given a public talk in about 2 years. So I might be rusty, but we're all here for a good time, right? Okay. So to get started, let me tell you a little bit about me. Logan kind of covered most of this, but I'm a fourth-year graduate student at Steward Observatory here at University of Arizona. And that means that I go up to, well, in my particular field, I go up to the telescopes on Cape Peak and I actually use the one next to the DESI collaboration that Parker was telling us about. So I get to look at her awesome telescope from my slightly smaller but still awesome telescope. For the past 4 years, I've been studying supernova. And when I'm not doing that, you can find me playing with my dog, shown here, Onyx, thinking about soccer, because I haven't really played it in a couple years, and wishing that every day was fall weather. But we're here to learn about supernova. And let me tell you about the first one ever recorded. It was called a guest star. We didn't really know what a supernova was at the time. So this one was discovered by the Chinese Han Dynasty in 185 CE in the Southern Gate Chinese constellation, which is actually between Centaurus and Circinus. I looked that one up. Circinus. It was shining for about 4 months after explosion, 8 months. And through observations, we learned that it was about 9,100 light years away. And today we can still see the remnants of the supernova explosion in the supernova remnant 185, shown here. And through the naked eye, we can't really see this supernova remnant, but when we point our telescopes at it, the area of it is actually 40% larger than the full moon. In this photo here, we have infrared data from NASA's Spitzer telescope and WISE telescopes, shown here in red and a little bit of yellow, with a little bit of background Milky Way dust, shown here in green, and all the foreground stars are in blue. So we need a lot of filters and we need powerful telescopes to see these sorts of things and learn from them. And then next was supernova 1054, I call it. This was discovered by the Chinese Song dynasty. And this guest star was so bright that it was believed to look like this near sunrise at the time. Clearly it doesn't look like that today, but imagine seeing the sunrise and you see this bright new, a guest star, because we didn't know what supernova were. Back then, so actually this supernova was lost to Western astronomers for a time. And in the 1920s, they saw a supernova remnant. Actually didn't know what a remnant was at the time, but they saw a supernova remnant. Some intern looked back at the historical records and determined from the Chinese astronomers that the remnant they were seeing in the 1920s must have been this guest star that exploded in 1054. Just a cool little fun fact for you. And the next we have supernova 1572. This one was discovered by Danish astronomer Tycho Brahe, or Tycho Brahe. Many different pronunciations, however one you want to mispronunciate, that's totally fine. One night, it was said that he noticed a bright and new unusual star. Now this was particularly shocking to him because since he was a boy, he knew the stars perfectly. No Game Boys around or Nintendo DS's. So he knew the stars perfectly, and so this was a big shock to him. He's like, that wasn't there before. But this was also surprising to him because this guest star went against the widely held belief that the universe was perfect and immutable. And believe it or not, this was also maybe not the most interesting thing that ever happened to him. So this is him, beautiful man. At 20 years old, he found himself in a duel against a fellow student in northern Germany. Now the actual reason for this duel has been lost to history, but the rumors state it was because of a mathematical disagreement, which is a little dramatic. But anyway, as a result of this duel, he actually lost the front part of his nose and was forced to wear a prosthetic on his face for the rest of his life, which you can sort of see in this photo, sort of not. The artists at the time were very kind to him because his family was very rich. But on top of that, this Danish nobleman was said to have dabbled in alchemy, employed a psychic dwarf to tell when his friends were going to die, and one day he even let his pet moose get so drunk that he fell down the stairs and died. So, given this man's foul temper, his distinctive physical appearance, and his eccentric habits, I have a question for the audience. So knowing everything that I just told you about him, I want to know, how did famous Danish astronomer Tycho Brahe die? Now, just in case, I don't know, I didn't know how big the screen was going to be, so I want to read it out loud for anyone who might not be able to see it. So A, did he die by holding in his urine for too long? B, was he felled by an atomic wedgie, one of those rare fatal wedgies? Or C, was he kicked in the chest by his pet horse? Now I'm going to count to 3. I'm going to see the first hand I see, and we'll see if you guess it right. 1, 2, 3. I saw you.
He held in his urine for too long.
That's right.
Yeah!
He held in his urine for too long. So history states that he was at a very fancy royal dinner, and politeness made him not leave the dinner table, which gave him a bladder infection and an excruciating few days afterwards. So this is for anyone with social anxiety out there. It is better to leave the dinner table than to hold in your urine for too long and get a bladder infection. So fast forwarding a few centuries to the 1930s, we have astronomers Fritz Zwicky, a nice looking man on the left, and Walter Batty on the right. Now these two men gave us the definition of a supernova. So they determined that these are not just guest stars. These are actually massive explosions in outer space of massive stars, or a runaway nuclear fusion in a white dwarf star. So basically, if you have a star and it explodes, this is a supernova. And before you ask, no, our sun is not going to go supernova anytime soon. And it will stay alive, hopefully, for the next few billion years. So there will have to be some other sort of global disaster that kills us all. But that was a sidetrack. By studying supernova, we can learn a lot about the universe. In fact, at peak brightness, or luminosity, as astronomers call it, supernova can actually outshine their entire galaxy. So think about that for a second. A galaxy can have 100 billion to 1 trillion stars in it at any one time. And just one star can be so dramatic that it dies and outshines everything. And we can use that to our advantage. So here I'm showing you a mosaic of supernova discovered by the Sloan Digital Sky Survey. And if you zoom in, like I've done here, to these 3 panels, this one on top, the supernova doesn't look like it has a galaxy behind it. But knowing what we know about stars and galaxy formation, we can assume that this star most likely died within a galaxy, meaning that there's a galaxy here we can't quite see. So we can use supernova to discover faraway galaxy. Now this was in 2006. We were discovering galaxies more and more with the James Webb Space Telescope. Woo! All right. All right, so not only can we use them to discover galaxies, but we can also use them to tell us the source of heavy elements in our universe. So here's a periodic table. You may or may not remember this from your science classes, but what this basically is just a table of all the elements we know in the universe. All right, we have hydrogen and helium in blue up top, and then a bunch of others that astronomers call metals. And this periodic table is a little bit different maybe than the ones you've seen, in that it's color-coded by the origin in space that it came from. So like hydrogen and helium up top, they're mostly in blue. They actually were created by the Big Bang. And if you go down to like the blue ones are created by the Big Bangs. And for the rest of these, if it's not blue, black, or red, it was created by a supernova or stellar processes. And specifically, the gold ones, the gold and white ones, are exploding massive stars or exploding white dwarfs. So those were the 2 tracks that Fritz Zwicky and Walter Batty determined created supernova. And so actually, if we think about this in a slightly different way, you know that famous saying by Carl Sagan, we are all made of star stuff? Well, if you break the human body down into the percentage of our elements, we are made of oxygen, carbon, hydrogen, nitrogen, and other. And most of those, except for hydrogen, were made within a star. And if you further break that down more towards the right and figure out where those came from, 74% of all that came from a supernova. So not only are we made of star stuff, but we're actually 74% supernova stuff. So there's a little addendum to that famous saying. That's mine. You can quote me. And at this point, you might be wondering, well, Rachel, the star doesn't go supernova and it goes directly into my body, so where does it go in between? Well, these supernova actually deposit these new heavy elements into the surrounding interstellar medium. And we can see this process of enrichment when we observe supernova remnants, like that nice bubbly one I had on my title screen. But they're not all so nice and bubbly. They can look like this, the Crab Nebula. And actually, there's a collaborator of mine in the crowd tonight wearing a Crab Nebula t-shirt. Thank you so much, Jeremy. That was a coincidence. Yay. And actually, this is the nebula that astronomers saw in 1920s that they were like, what the heck is this? And then they looked through the historical records and they figured out that that was supernova 1054. That's kind of cool. Or they can be even scarier looking, like this red spider nebula, which has completely abandoned the idea of cute and bubbly, unless you like spiders. Or they can be like this butterfly nebula, which is a little cuter. And so all of these supernovae out here are really just adding new ingredients to the universe. So if we think about it like a pizza, where the pizza dough is everything created by the Big Bang, then supernova actually give us those yummy ingredients on top, like the tomatoes, the mozzarellas, and the basil. And not only do they give us those ingredients, but they actually trigger the formation and the heating of the pizza itself. And voila, we have a universe full of hot and ready pizzas. Yeah. But unfortunately, this is not the reality we live in. But what actually happens is pretty cool too. Coming back to astronomical terms, what this means is that a supernova can and will cause a cloud of nearby enriched interstellar medium to collapse and form new stars, like in this Orion Nebula here. And when these areas are creating new stars, these are called stellar nurseries. That's pretty cool. And the next is that we actually use supernova to discover that our universe is expanding at an accelerating rate. So it's going faster and faster and faster. So if you think of this as time, and if we imagine this is the universe, so it started as a really fast bang, and then it kind of chilled out. And then towards the end here, towards us, it's actually flaring out a bit. So the universe is accelerating its expansion, and we use supernova to do that, like Parker told us. We use supernova as standard candles. And we use those to discover that there's dark energy in the universe, which is not dark matter. You guys remember that? And it's almost 70% of the energy density in the universe. So we are just a little bit of what's going on around here. And it seems like there's almost nothing we can't learn from studying supernova. But today, one of the biggest questions we have as a supernova astronomer specifically is where do supernova come from? And I know you're thinking, well, didn't Fritz Zwicky and Walter Batty solve that problem in the 1930s? Well, no. They figured out that supernova are the explosion of massive stars, but they didn't tell us anything really before that. And as a scientist, we kind of want to know everything, and we don't actually know every single step before that explosion, which would change the way that we think about the universe in a little more technical terms. And so with the rapid advancement of telescopes today, we are able to discover hundreds of supernovae per year, which looks a bit like this when we visualize what that would look like on the sky. So if we took the entire celestial sphere around us and projected it onto a 2D map and showed you the supernova discovered over time, you can start to see the entire sky populate a little more and more. And then we hit the age where telescopes are robotic. We start seeing more and more. And boom, now we have all these different surveys and the sky just gets so cluttered. There's SDSS, light blue, and wow, DES, dark energy survey, which is kind of the former DESI. All right, so with such a large data set, it is possible to uncover the subtle differences between supernovae now, leading to the inevitable practice of supernovas categorizing everything in an increasingly complex manner. So it sort of looks like this, but I actually won't make you memorize this or learn about this tonight. Instead, I want to introduce to you a way in which astronomers use to distinguish between supernovae when we discover them in the sky. And that is by using something called a light curve. This is just brightness over time. And so remember all those elements we talked about earlier where supernova create these heavy elements in the universe? Well, some of them like to shine, depending on how much energy that supernova has given it. And so certain elements will shine brighter or longer than other ones. So here, the element nickel is causing a steep light curve. It shines really bright, and then it actually decays into other elements. But it has this really bright and steep increase in brightness, and then it starts to fade. And then cobalt takes over. And the cobalt gives it a slightly flatter light curve. And eventually causing the light curve to be like this for a few months. So if you imagine this is time on the bottom, this is a few months of time. Supernova shine for quite a bit. And by studying and comparing these light curves, we can uncover what elements are created by certain types of supernova, and which in turn tells us how hot the explosion was and what elements must have been present before the supernova explosion. So if you imagine a star out there in space ready to explode, there's certain elements around it. And by exploding the star, we can actually see some of that surrounding material as well. And so for the past 4 years, my research has actually been about uncovering the elements that were there before explosion, using techniques like light curves. And now I want to leave you with a little bit of wonder about the universe. So the estimated rate of supernova is about 1 to 2 per century in a typical galaxy. Now this is much higher than the actual observed rate, which implies that a portion of these supernova have been hidden from us behind the interstellar dust, which is visible here in this picture of the Milky Way as these dark patches. So if we didn't have dust in the way, the Milky Way would be super bright. But since we have all these dust, we can see these dark patches. But if we use techniques like using different wavelengths, we can see that this dust that was previously dark to us in the optical actually shines in the infrared. And so there are new telescopes being built out there that will eventually show us what's behind all the Milky Way dust. And hopefully the next Milky Way supernova that goes off won't be shrouded and we'll be able to discover it. Which is where I have my final question, which I'm not showing you yet because you all read it too fast last time. So a couple years ago, you all may have heard of Betelgeuse in the news. That is, for some reason, it was dimming, and astronomers didn't really know why. And they thought maybe it's going to go supernova. Well, Betelgeuse is actually this red star in the left shoulder of Orion, the constellation that everybody knows and love, right? And so what I want to ask you, the solution to that problem a couple years ago was that Betelgeuse did not go supernova. And we don't really know when it's going to go supernova. But that's what I want to ask you. I want to gauge you all on how optimistic you are. So when do you think Betelgeuse is going to explode? Is it going to be A, within 1 year? And astronomers are going to be able to discover and study the closest supernova in a long, long time. Is it going to be B, within 10 years? Maybe I'll still be around studying these, and I'll be the one to study them. Or is it C, not for the next 100 years? So this isn't like a first person to raise their hand one. Somebody already got their prize. So I want to see how many people think it's A. Yeah, so optimistic. Thank you. How many people think maybe B? Got a couple more out there. That's cool. I like ya. How many think C? Oh, man. All right. All right. So we don't have a lot of optimistic people out there, but that's okay. More people after me will be around to study these supernova. And so I want to thank you for having me tonight. Hopefully you learned a little bit about supernova. I love these things, and I want you all to have a great time.
Man, I want Betelgeuse to blow up in my lifetime so bad. I voted for 10, even though it's probably over 100. Questions for Rachel?
What's your favorite nebula?
Oh, wow. My favorite nebula is probably the Eagle Nebula. I don't have a picture of it, sorry, but it has the pillars of creation in it. And it's actually the one my dad likes a lot. So I like it because my dad likes it.
I'm a Helix nebula kind of guy.
Oh, Helix Nebula is cool too. Nebula, supernova remnants are dope. They make cool shirts. Oh, we got any other questions? Yes.
Heaviest element created by a supernova. What is it?
All right, so heaviest element created by a supernova. The one that I know of is gold. Wait, let me go back to the periodic table. Heaviest natural element, but is that a neutron star? So exploding massive stars. Let's look at the table. Exploding white dwarf looks like rubidium. Maybe some, what is that? Kryptonite? No, it's chromium. Krypton. All right, those ones. But I thought gold. I think a while ago it was discovered that gold is actually made by merging neutron stars. But that's pretty cool too. One more question. Okay, thank you everyone so much for coming out tonight.
Woo! Thank you, Rachel. That was really great. All right, so that wraps up SpaceDrafts number 69. Our wonderful undergrads will still be out here with telescopes. I'm not sure how long they're going to stick around, but they're still out here now. And don't forget to tip your bartender. And don't forget to buy a lovely SpaceDrafts sticker. And don't forget to follow us on Facebook and Twitter and find out about our next show. We are trying to host these every third Tuesday of every month. So look for us again this time in November. We are talking about maybe trying to do something for James Webb because that's coming up, the James Webb launch. Hey, December. So yeah, so keep an eye out on the social medias and join our mailing list if you have not already. And have a great night. Great job.
I need to buy a sticker before I leave.
Yeah. Oh, sorry. Thank you, Lily, for taking charge of that.
So good.
And
Video ceremony.
yeah.